Today we are discussing circular motion, especially uniform circular motion. I am giving motion, uniform circular motion to this medical tap using this cloth, we can say thread. This way, observe this. The speed is almost constant. So medical tap is performing uniform circular motion. Yani the motion of this body is on a circular path with constant speed. But what about its velocity? Is it constant or not? No. Yes. Because of, suppose in this situation, this is the center, or this is the at certain moment its position. So its velocity is in the direction of tangent. So here velocity in this direction. But after certain moment, the velocity in this direction. So magnitude is constant, but by direction velocity is not constant. See the figure. Particle is performing uniform circular motion on this circular path of radius r. At certain instant it is here. So velocity is in the direction of tangent. This one is the velocity v1, say v1. After a short while, it reaches to point q. But at that moment, the velocity is in this direction. These two vectors are having same length, we have considered, because of the speed is constant. But at time t, the velocity is in this direction, or at time t plus delta t, it is in this direction. So direction changes. So accelerated motion is there because of velocity changes. Now we want to find this acceleration, but acceleration is vector quantity. Agree?
Yes.
So we want to find direction as well as magnitude. But by common sense, suppose I am performing uniform circular motion. I am giving uniform circular motion to this medical tap. Suppose its speed is constant, but every time, at every moment, every instant, this thread applies force on this medical tap, and this thread applies force to this medical tap in the direction of lengthwise. It can exert force lengthwise only. So at any instant, suppose it is here, the force is in this direction. Suppose it is here, force is in this direction. That is towards center. And we know that F equal to ma.
Yes.
So the direction of force, it is the direction of acceleration because of F equal to ma. And mass is scalar quantity. So direction of force, it is the direction of acceleration also. Now, using geometry, suppose at time t particle is here, at time t plus delta t particle is here. So this one is v1 and this one is v2. So this one is v2. We have drawn these two vectors from same point. So this one is v2, so this one is v2. I have tried my best. See, this and these are parallel, and v1 are parallel. So this is v1 vector, this is v2 vector, and this one is question mark. So from the triangle law for vector addition, v1 plus question mark vector equal to v2 vector. So v1 plus question mark equal to v2. So question mark vector is v2 minus v1. And v2 is final velocity in our time interval.
Yes.
This is initial velocity. So it must be change in velocity, delta v. So delta v is a vector quantity and it is in this direction. But we have taken this path from P to Q. So the average acceleration, for average acceleration, we have to put this vector at midpoint of this chord, midpoint of this arc. So it suggests average acceleration in our time interval is towards center. Okay? But if we take very small time interval, this is the photograph at time t. But after a very short while, delta t is very small, very small. So the second position may be here because we have taken smaller time interval. This time initial velocity is v1 as it is, but the final velocity is not v2. Now this final velocity is slightly slanted v2 dash, say v2 dash. So in this time interval, if we find delta v, so again v2 dash is this one is v2 dash, and v1, this one is v1. So if we consider this vector double question mark, so from triangle law for vector addition, v1 plus double question mark equal to v2 dash. So double question mark is v2 dash minus v1. So it is also change in velocity in our time interval. Now the time interval is very small, so we can say delta v dash. But it is very small. If we take very small time interval, infinitesimally small time interval, then we can say dv, microscopical change. So this one, observe the direction. Now these 2 points are P and Q dash. So if we put this vector midpoint between these two, midpoint, arc midpoint, so it also suggests towards center. So geometry also suggests instantaneous acceleration is also towards center. So force must be in the direction of center at every instant of time. Now consider these two triangles OPQ. This one is the R1, initial position vector at time t. This is R2, position vector of the particle at time t plus delta t. So this must be a vector connecting initial position to final position is called displacement vector. So it is delta R, displacement. When it is here, the velocity is in this direction. When it is here, velocity in this direction. So for this, consider this triangle V1, V2 and delta V. If angle between R1 and R2 is theta, then angle between V1 and V2 is also theta. Because of R1 is rotated by 90 degree angle, R2 is also rotated by 90 degree angle. Both the branches are rotated in the same sense, same direction, by same angle. So angle between them remains same. So this one is theta, then this one is theta. Here we have considered uniform circular motion, that is speed is constant. So mod V1 equal to mod V2 equal to V, which is the speed of the particle, we can take. And this is the circular path. So as a position vector, R1 and R2 are different, but by magnitude they are radii of the same circle. So mod of R1 equal to mod of R2 equal to R. So these two sides are equal because speed is same, angle, this angle same, these two sides are also equal. So by SAS postulate, side, angle, side, these two triangle O dash, P dash, Q dash and triangle OPQ, similar. And we know that in similar triangles, sides are in same proportion, ratio remains same. So this delta V by V, we are considering magnitude only. So delta V by V equal to delta R by R. By subjecting delta V, we get V by R into delta R. Okay? But if we take very small time interval, so considering this triangle and this triangle. It's very small. This is d theta. So this is also d theta. So under limiting condition, that is delta t tends to 0, we have taken infinitesimally small time interval. So this delta v converts dv. V by r remains same. V is the speed of the particle. And speed remains same. And if we consider very small time interval, then displacement vector and distance overlap each other almost. So by magnitude they are same. Almost. But if you consider very small time interval, then displacement and distance remain same. So this is the speed of the particle. dv is v by r into dr, dividing both the sides by dt. So dv by dt equal to v by r into dr by dt. But dr by dt is speed. Speed is constant. And it is v. So a is v by r into v. So a is v square by r. By magnitude, the acceleration is v square by r. And we have discussed direction already. It is towards center. So we have obtained acceleration of the uniform particle performing uniform circular motion is towards center and having magnitude v square by r. It is called center seeking acceleration because it always remains towards center. It always remains towards center if a particle is performing uniform circular motion. But from that uniform speed, I want to increase. Suppose initially the velocity, speed of the particle, that is medical term, is 20 centimeter per second, for example. Okay, but from that speed I want to increase up to 30. So for this, observe my position and effort this way. Suppose the speed is constant or it is 20 centimeter per second, but I want to increase at another level, say 30. So for this, I have to displace my force not towards center. See this. So at certain moment when medical tap is here, this here, and center is here, so at a time I have moved my hand this way. Now the force is in this direction, not towards center. Center is same. It is moving on the same circular trajectory, but the force is toward this. And this force has two components. This one is centripetal acceleration and this one is tangential acceleration. And this gives increment in speed. Otherwise, we can't increase the speed of the particle. So that is, if a particle is performing uniform circular motion, acceleration is towards center. But if a particle is performing circular motion with increasing speed, this way, so acceleration must be here. Particle is performing this way, and it is performing circular motion on the same track, on the same radius, but it is performing circular motion with increasing speed. So the actual force is in this direction. It has two components. Acceleration is also in this direction. It has two components. This one is tangential acceleration and this one is centripetal acceleration. Sometimes it is denoted as radial acceleration. And this acceleration is responsible for circular motion. And this acceleration is responsible for increment in speed.